Hi, this is Qiaochu at Lehigh University. For today's video, we are going to talk about the homework for week 15. Let's take a look at the first one. It's a confined aquifer, has transmissivity equals to 500 meters squared per day, and the storage coefficient equals to 0.0005. Wells 1 and 2 completely penetrate this aquifer and will be pumped at a constant rate, 600 cubic meter per day and 1400 cubic meter per day respectively. Pumping will start in both wells at the same time. The distance between observation well and well 1 is 400 meters, and the distance between the observation well and well 2 is 500 meters. We need to determine how long can the two wells be pumped without exceeding a 1 meter gel down limit in the observation well. And at this limit was the gel down contribution of each well. In other words, we need to calculate the S1 and S2 when the total gel down S it equals to 1 meter in the observation well. Before we solving this problem, let's analyze it first. Because we know the total gel down it equals to 1 meter. By applying the equation 7.29, the total gel down should equals to the gel down contributed by each well. In this problem, the capital M here it equals to 2, and J indicate the different well. So the S should equals to S1 plus S2. But we do not know the value of the S1 and S2. So to calculate these two values, we need to use the equation 7.26. The total gel down from each well is related to the transmissivity, the flow rate, and the well function. We already know the value of the transmissivity and the flow rate, but we do not know the value of this one. Therefore, we need to apply the table 7.3 to determine the value of the well function. The well function is related to the U here. The U indicates the dimensionless parameter. And by applying equation 7.27, this parameter is related to the distance and the storage coefficient, the transmissivity, and the time. In this equation, we already know the value of the distance, the storage coefficient, and the transmissivity, but we do not know the time it may take. Therefore, we can make assumption and bring the value into this one, and to get the value of the dimensionless parameter, and then determine the well function. Then to calculate the gel down from each well, and calculate the total gel down. So which means that we can try different values of T until the total gel down equals to 1 meter. So let's solve this problem. We'll use this table to help us solve this problem, and we will use T equals to 1 and the first well as a demonstration to solve this problem. Let's calculate the dimensionless parameter in well 1 first. Based on this equation, because we already know the value of these parameters, because in this table we assume that it may take 1 day, therefore the T here it equals to 1. And we can get the value equals to 0.04. And we can use the same equation to fill out the values in these two columns. And then we need to calculate the value of the well function. Because in the previous step, we got U1, it equals to 0.04. It equals to 4 times 10 to the power of -2. Therefore, based on this table, we can find its the value of the well function equals to 2.681. And then we can fill out other blocks. The next step is to calculate the drawdown from each well by applying equation 7.26. And after we bring these three values into the equation, we can get the drawdown. It equals to 0.26. After we got the drawdown from each well, then we need to add them together to calculate the total drawdown. This problem asks us to determine the value of these parameters when the total drawdown equals to 1 meter. Therefore, we need to, the 1 meter is between these two values. Therefore, we need to try different t between 2 days and 3 days until the total drawdown it equals to 1 meter. So after we try several times, we find that when the t equals to 2.2, its total drawdown equals to 1 meter. Therefore, we know that after 2.2 days, the drawdown limit at the observation well is reached, with S1 equals to 0.33 meter and the S2 equals to 0.67 meter. Now let's take a look at the second problem. In this problem, we know the transmissivity it equals to 450 square feet per hour, and the storage coefficient it equals to 0.0005. On the right-hand side is a plot. In this plot, we can find the location that we are interested in is here. It's represented by the dashed line. And for the well 1, we know the flow rate is 207 gallons per minute. And the distance from the well 1 to the location that we are interested in is 322 feet. And the well 1, it pumping 3 days. It equals to 72 hours. And for well 2, the flow rate, it equals to Q1. It's 207 gallons per minute. And the distance from the interested location to the well 2 is 279 feet. And because it told us the second well will start a day and a half after the first well, so the pumping duration for well 2, T2, it should equals to T1 minus 1.5 days. It equals to T1 minus 36 hours. So in this problem, we need to calculate the drawdown at a critical location in a confined aquifer. And from the plot on the right-hand side, we can find that the S it equals to S1 plus S2. S1 is the drawdown generated by well 1 at the critical location, and S2 is a drawdown generated by well 2 at this location. So let's calculate the S1 first. So for well 1, we need to calculate the dimensionless parameter by applying equation 7.27. The R1 is 322 feet. The storage coefficient is 0.0005, and the T transmissivity is 450 square feet per hour, and T1 is 72 hours. Then after we bring these values into this equation, we can find U1. It equals to 4 times 10 to the power of minus 4. So the next step, we need to use U1 to determine the value of the well function by applying the table 7.3. So we divided this value into two parts, 4 and the second part 10 to the power of minus 4, then we can find the intersection is at 7.247. So based on this table, we can find the result, the value of the well function is 7.247. Then the next step is to calculate the drawdown generated by well 1 by applying the equation 7.26. After we bring this value, the transmissivity, the flow rate, and the well function into this equation, we can get the drawdown, the S1, it equals to 2.13 feet. Then we calculate the drawdown provided by well 2, following the same procedure. So first, we need to calculate the U2 by applying equation 7.27. And then, based on the table 7.3, we determine the well function. And next, we use the equation to calculate S2, it equals to 2.01 feet. And the last step is to add these two drawdown together. So the total drawdown S, it equals to S1 plus S2. It equals to 4.14 feet. Now let's move on to the third problem. In this problem, we know the transmissivity is 40 square meter per hour, and the storage coefficient is 0.00025. And the distance from the location that we are interested in to the pumped well is 50 meters. And we pumped water 3 days. And at the initial, the time is 0 and the flow rate is 0. And we pumped water in 2 different flow rate. So at the first 2 days, we pumped water with a flow rate 800 cubic meter per hour. And in the remaining times, we pumped water with a flow rate 500 cubic meter per hour. We need to determine the drawdown at a critical location in a confined aquifer. Because in this problem, we have 2 different flow rates. So let's consider the situation when the Q equals to 800 cubic meter per hour. Let's calculate the U1 by applying equation 7.25. The distance R is 50 meters. The storage coefficient is 0.00025. And the transmissivity is 40 square meter per hour. And we know currently here the T is a total pumping hours. It should be 72 hours, and T0 is 0. After we bring these values into the equation, we can get U1 is 5.43 times 10 to the power of minus 5. Then, based on the table 7.3, we can determine the value of the well function. It should because the U1 is between these 2 values. Therefore, we know that the W, the well function of U1, it should between these 2 values. Therefore, after the interpolation, we can find the value of the well function. It equals to 9.248. Then let's consider the second scenario when the flow rate equals to 500 cubic meter per hour. Following the same procedure, we can calculate the U2. It equals to 1.63 times 10 to the power of minus 4, and then use the table 7.3 to determine the value of the well function. And we also need to do an interpolation in this step. So we find the value of the well function is 8.196. Then we can calculate the drawdown by applying equation 7.24. We know the initial flow rate is 0, and the flow rate Q1 is 800 cubic meter per hour, and Q2 is 500 cubic meter per hour. And we just calculate the W of U1, the well function 1, it equals to 9.248, and well function value of well function 2, it's 8.196. After we bring this value into the equation 7.24, we can determine the draw down. It equals to 9.83 meter. Let's move on to the problem 4. The characteristics of a confined aquifer are required. A pump test is conducted at a flow rate of 5.4 cubic meter per hour. Draw downs are measured at an observation well located 18 meter from the pumped well and are tabulated below. We need to determine the aquifer transmissivity, the storage coefficient, and the draw down after 50 hours. To solve this problem, the first step, based on the given information in the table, we generate the plot on the right-hand side, and in this plot, we present the time in logarithmic scale. Based on the equation 7.42, we can calculate the transmissivity. In this equation, we already know the flow rate. It equals to 5.4 cubic meter per hour, but we do not know the value of this one, the delta degree S. This term represents the increase in draw down per log circle of time, and it equals to the delta S divided by the log T. And for any log circle of T, the delta log T, it equals to 1. Therefore, we need to find the delta log T in this plot. From this figure, we know that the log 1, it equals to 0, and log 10, it equals to 1. So the log 10 minus log 1 is a delta log T, it equals to 1. So based on this information, we can determine the delta S. It equals to the delta degree S by applying the 1.61 minus 1.09. So we know it equals to 0.52 meter, and we already know the flow rate, so we can determine the transmissivity. It equals to 1.9 square meter per hour. Next, we can calculate the storage coefficient by applying equation 7.43. In this equation, we know the transmissivity is 1.9 square meter per hour, and the distance r is 18 meter. We need to determine the T0. Let's back to the plot. In this plot, the line here is generated by connecting these 2 points together and then extend the line to make it intersect with the x-axis. And the T0 is the time when the draw down equals to 0. It's the initial point. So from this plot, we can read the T0 is close to 0.0082. Okay, so currently we can determine the storage coefficient. It equals to 1.08 times 10 to the power of minus 4. Then we can determine the draw down after 50 hours by applying equation 7.44. And in this equation, we know the flow rate is 5.4 cubic meter per hour. Transmissivity, we just calculated, is 1.9 square meter per hour, and the distance is 18 meter. And the storage coefficient is 1.08 times 10 to the power of minus 4. And because the T here is after 50 hours, so it equals to 50 hours. Then we can get the result. The drawdown after 50 hours is 1.97 meter. Now let's move on to the problem 5. A factory is pumping flow rate 1.55 cubic feet per second from a confined aquifer, 5,660 from a fully penetrating river. An observation well located between the river and the pumped well, 100 feet from the river, and 5,560 feet from the discharge well. And the drawdown at the observation well is 0.333 feet. Based on the given information, because we know that at the boundary, the surface here is connected to the surface of the river, so the drawdown at the point we are interested in, it equals to 0. Based on the plot on the right-hand side, we can also know that the line here represents the drawdown with boundary, which means the drawdown in reality. And the dashed line here represents the drawdown without boundary, which means that if there is no boundary, there should have a drawdown at this point. So when we do not consider the boundary, we should assume that there is another imaginary recharge well on the right-hand side with the flow rate equals to negative 1.55 cubic feet per second. And its location is 5,660 feet from the point that we are interested in. And also, it's the distance between the recharge well to the observation well is 5,760 feet. Then we can, based on this information, we can bring this value into the equation 7.12a to calculate the drawdown at the point that we are interested in. In this equation, we only have one unknown, is a transmissivity. So the S here, it equals to 0 feet, and the drawdown as an observation well is 0.333 feet. And we already know the flow rate at the well A and well B, and the distance to the observation well, and the distance from the point that we are interested in to the well A and well B. After we bring these values back into the equation, we can get the transmissivity. It equals to 0.0262 square feet per second. Now let's move on to the last problem. A pump is required to dispose of the water seeping through the earth levee. The water level behind the levee is 30 feet. The length of the levee is 980 feet. The permeability coefficient of the soil, the K, it equals to 7.5 times 10 to the power of -6 feet per second, with a porosity phi, it equals to 0.4. We need to determine the seepage rate, Q, in gallon per minute using the flow net provided. So based on the plot on the right-hand side, first we could determine the number of flow channels to count the number in vertical, to counting the number of the blocks in vertical. It equals to 4. So the M, it equals to 4. And then we can determine the number of cells along the flow channel. The number of blocks in horizontal, it close to 30. So the N, it equals to 30. Then we can calculate the seepage rate per unit width of the dam, the small q, by applying equation 7.56. The value of K and H are given, and we just count the number of M and M. Therefore, we can get the seepage rate per unit width of the dam is 3 times 10 to the power of -5 cubic feet per second per foot. Because we need to determine the value of the capital Q here. So we need to use it equals to the Q, small q times L, the length. Because the length is 980 feet, then we can determine the seepage rate is 13.2 gallon per minute.